In this video, we're going to be going through week 8 of Physics 259, which talks a bit about electric fields and how they relate to electric currents and how they influence electric circuits. This discovery was first made by Hans Ørsted, who's the first to find a relationship between electricity and magnetism in 1820. In his experiment, he had a compass and noticed that once he connected a current-carrying wire over the compass, that the compass dial started to move. And compasses only move in the under the influence of a magnetic field. So therefore, he deduced that this current-carrying wire was inducing a magnetic field that was affecting this compass. So all magnetic fields are produced by moving charges. So it's important to note some properties about magnets. All magnets have a north and a south pole, which you may already know, and it flows from north to south. So if we were to draw lines, they would look something like this. So out of our north pole and into our south pole. And a key detail about magnetic fields is that they continue to flow through the magnet, right? So they're continuous. So we're going to talk about first right-hand rule for our electric fields. So this is to determine the direction that a magnetic field is produced. So direction of magnetic field in a current-carrying wire. Okay, so if we were to use this example here, we want to find whether there is an attractive or a repulsive force in each of these directions shown for these wires. So if we want to represent into page, it would look like an X. And if we represent a magnetic field coming out of the page, we'd represent it with a dot. So this is kind of like Coulomb's law, like repel, opposites attract. So if we have two sets of magnetic field lines that are next to each other that are both pointing out, then that means that they will produce a repulsive force between them. However, if we have two opposite sets of lines, then this will produce an attractive force between them. So to use our right-hand rule, I'm just going to come back up to this part here. You're going to point your right thumb with current flow. And then you're going to curl your fingers around. And this represents the magnetic field. So in this example, if we line our hand like this, we see that it will wrap around like this in this example. Oh, sorry, that looks gross. Right? So if this is our right hand, our thumb points with the flow of the current, and our fingers are going to curl around. So in this case, since our fingers point into the page here and come back out here on the other side of that wire, And this means we have a set of magnetic field lines that look like this. Right, where it goes into the page, then back out of the page. So it kind of circles around it and comes back out. Now if we do the same for the other side, we would see that we would get the same results. And when we look at the region between these two wires, we see that they have opposite directions. So in this case, this would be an attractive force between the two wires based on the magnetic field that they produce. Now, if we run this through with our other example, so we know that this wire is going to look like this. Right, and now if we do right-hand rule, if we point our thumb downwards, so we're going to start with our hand like this. So this is the back of our right hand. So it'll start pointing down. And then when we curl our hands around it, we would see that they first enter in on this side of the page when we first curl it, and they are going to come back out on this side. So now that we have two of the same directions of field in between our two wires, this would be a repulsive force that's developed between them. Okay, so that is our first right-hand rule on how to apply it. So next we're going to talk about how we can find our magnetic force caused by our field, so it's represented with this equation here. This is FB equals Q times V with the cross product of B. And cross product we determined using this method, where our VI would be here, our VJ, VK component would be here, and our BI, BJ, and BK component would be there, right? And we would take the determinant using this kind of matrix. And we know from cross product, this is also equal to saying that the magnitudes of each of our variables times our sine theta, where theta is the angle made between our V and our B, right? And that is an alternative form to write this equation in. So we talked about cross product formulation in the previous lectures. This also uses a right-hand rule, where we're going to point our fingers along the first vector, which is our velocity, in this case, which is our V. And we're going to curl our fingers towards our second vector, which is B. And our thumb is the resultant vector that is formed from our cross product, which is our FB, right? So again, starting with our velocity, point your fingers along that line and curve your fingers towards the second one, which is our magnetic field. Force is going to be produced as a result with the thumb. Okay, so if we were to do an example of this, let's first find where our force is, and we're going to find magnitude and direction of force. Okay, so let's put our right-hand rule to use. So if we start by pointing our right hand with our if we start by pointing our right hand along our velocity vector, and we curl it towards our B, Right, so our fingers are going to curl this way. We see that our thumb is going to point into the page. So we already have our direction for our force, which is going to be into the page. Okay, and now we want to find the magnitude of our force, which we can use our equation for, which was Q, and then V cross product for B. And let's use the other form. Let's use Q, the magnitude, each one, sine theta. Okay, so the angle that these two make is a 90-degree angle. They are perpendicular to each other. So that's what's going to be in our theta, so we already know that. We know our charge of our particle, which is a proton. We have our velocity, and we have our force. So, given that, we can use these values. So this is 1.6 times 10 to the negative 19 coulombs for our charge. Velocity is 1.5 times 10 to the 3 meters per second. And we have 15 times 10 to the negative 3 Teslas. And sine 90 is just equal to 1. So when we plug in these values, this is going to give us 3.6 times 10 to the negative 18 newtons in our, and that's into the page, is our direction. So now, if we did this with an angle now, so now that the angle formed between them is, now that the angle formed between them is this angle right here, which is, so that is 90 minus 26. This is 64 degrees between them. Okay, so we can use our same equation. Where the angle between our magnetic field and our velocity is 64 degrees. We can plug these values in. So we have a proton, so that's 1.6 times 10 to the negative 19. Velocity is 8.5 times 10 to the 2 meters per second. We have 20 times 10 to the negative 3 Teslas. Sine 64, and we want to find the direction. And again, if we line up our fingers along the direction that the proton is traveling, and we curve towards our magnetic field. So if we curve our fingers like that, our force is pointing into the page. So we're going to put this in the negative k hat direction. So this is going to be 1.6 times 10 to the negative 19 times 8.5 times 10 to the 2 times 20 times 10 to the negative 3 times sine of 64. And this is equal to 2.447 times 10 to the negative 18 newtons in our negative k direction, which is into the page. Okay, so this is kind of just a review for our right-hand rule for cross-product formulation and what vectors form as a result of two vectors. Okay, so now we're going to talk about cross fields. And this is a region where both magnetic and electric fields are present, where moving charges experience both electric and magnetic forces. So using this equation here, we see that our total net force is the result of our electric force plus our magnetic force. So if we were to use this in an example, so this case only really occurs if we have a specific scenario where we have uniform electric and magnetic fields being formed. So if we had a parallel plate to give us our uniform electric field, we know that it points from positive to negative, right? And let's say we also had a uniform magnetic field pointing into the page. So if we had let's call this a proton, traveling in this direction undeflected, let's first find I should put velocity. Let's find where our magnetic force will be pointing. So if we use our right-hand rule, start with our hands pointing in the direction of our velocity. And once we curl them into the page where our magnetic field is, we see that our force points upwards. Right, so that is our magnetic force. So I'm going to just draw a free body diagram of our particle. And if we want to keep this undeflected, that means the influence of our electric force is pointing downwards. So in this case, since we're pointing in opposite directions, if we were to write the net force in this system, this would be our magnetic force. Sorry, let me switch around the colors here. And this is minus, since it's in the opposite direction, our electric force, which is Q times our electric field. All right, moving on, we're going to talk about circular motion of a particle in a magnetic field. So if we were just to isolate this motion here, right, where we start with our, in this diagram here explains it better, where we start with our fingers pointed in the direction of the velocity, and we curl our fingers into the page for our magnetic field lines, we see that our force points up. Now, if we start at this section here, we see that it would also point up relative to the direction of travel here. If we do that continuously until it forms a circular pattern, we see that the force always points inwards. So the magnetic force on the charge is directed perpendicular in its motion. So it's always going to be perpendicular relative to the motion of travel. That's what it would look like in a circular motion. Okay, so to find the radius of a circular path, we're going to use the equation for centripetal force, which is mv squared over r, where m is our mass, v is our velocity, and our r is the radius of our direction of travel. And we want to make this equal to our magnetic force. So when we do that, we get mv squared over r equals qvb sine. And one of the v's is going to cancel out on our left side. It's going to completely cancel on the right side. So that gives us, once we isolate for our radius, r equals mv over qb. And a period is how long a particle takes to complete a circle. So we're going to use our velocity, which is distance over time, and our distance in this case is the circumference of a circle over our period in place of our time, and that makes t equal to 2 pi r over v. And if we make our r equal to this mv over qb from our previous equation here, we can write it out in this form. Angular frequency is calculated by 2 pi over our period, and this is the rate at which the angle is changing as it goes around the circle. Okay, so in this example, we have a charged particle with a mass of 3.17 times 10 to the negative 27 kilograms, moving in a circular path through a magnetic field of 4 milliteslas over a period of 31.1 microseconds. So what is the charge of the particle? So we know that FB is going to equal our centripetal force. So this is mv squared over we'll start with this first. This is QVB sine. And this is equal to mv squared over r for our centripetal motion. And we want to isolate for q. So let's move this to the other side. So then q is equal to v and b. And one of those v's is going to cancel. So this is mv r sine theta b. Okay, and once we have that, we can make this equal to our equation that includes our period, which we will use here. So we can use this equation here. So T is equal to 2 pi m over qb. Isolate for q. This gives us this equation here. So now we have everything that we need to solve. Our mass is 3.17 times 10 to the negative 27 kilograms. It's 4 milliteslas, so this is 4 times 10 to the negative 3 teslas. And our period is 31.1 times 10 to the negative 6 seconds. And this gives us a charge equal to 1.6 times 10 to the negative 19 coulombs, which we know to be either a proton or an electron. So we want to find what our charged particle is. So we're going to direct our hands along so if we direct our hand along the velocity and we point our fingers down into the page, this gives us a force pointing upwards. And we know from our circular motion that our force must point into the circle. So if we did that with our right hand, I forgot to specify that if you perform the same operation with your left hand represent negative particles. So since we know protons are positive particles and electrons are negative, and our electron, if we use our left-hand rule in this case to formulate the cross product for our negative particle, so we point our left hand like this along V and curve it into the page. With our field lines, we see that our force points into the circle. So this means that this is an electron, right? Because using left-hand rule, it satisfies our circular motion, where centripetal force points into our rotation. Okay, so now we're going to talk about mass spectrometers, which is an apparatus that uses circular motion of charged particles in magnetic fields to measure their mass. And in this simulation shown, we have an electron moving in a 100 millitesla magnetic field at a speed of 200 kilometers per second. Let's convert this. So in a kilometer, we have 1,000 meters. So this is equal to, so it's 200 times 1,000. It's 200,000 meters per second. And we want to find the mass of our particle. So we're given our, so we have charge, we have mass. Actually, not necessarily. I'm not sure if our mass is different. Sorry, we need to find our mass. Sorry, we have our charge, we have our field, and we have our radius. So if we have our charge, field, and radius, and we're looking for our mass, so we have charge, field, radius. Do we have our speed? Yes, we do. So we're going to use this equation here. So this was B is equal to our centripetal force. This is QVB. And they are perpendicular, so I'm not going to include the sign. And this is times mv squared over r. Okay, this is going to go away. This is going to cancel out. So this is QB equals mv over r. And isolating for our mass, this gives us QBr over v. So now if we use this to calculate our mass, so our charge is 1.6 times 10 to the negative 19. And this was given to be 100 milliteslas. Our radius is 10 centimeters, so that's 0.1 meters. And this is over our velocity, which is 200,000 meters per second. So that gives us a mass equal to a mass of 8 times 10 to the negative 27 kilograms. All right, moving on, we also have a case where our circular motion has pitch to it. In that case, it wouldn't just produce a flat circle in our xy plane. It would actually produce a helix that gradually spirals upwards or downwards, depending on the motion. And we can represent this using this equation here. Where p, our pitch, is the distance between our coils. So we can represent it using this equation here. Or substitute our time for our period and substitute period with our equation that we determined above to represent it here. Okay, example 3. A proton moves through a 50 millitesla uniform magnetic field with a velocity of 2.5 times 10 to the 3 meters per second at an angle of 75 degrees. So what is the pitch of the path? So using our equation above, we're going to use P is equal to V cos theta times 2 pi mass over QB. So this is equal to, so it's 2.5 times 10 to the 3 angle of cos 75. This is times 2 pi, and our mass of our proton, which is 1.67 times 10 to the negative 27 kilograms. our charge is 1.6 times 10 to the negative 19. We're given our uniform electric field, which is 50 milliteslas. And this makes our pitch equal to, so this is 2.5 times 10 to the 3 times cos 75 times 2 pi times 1.67 times 10 to the negative 27 divided by 1.6 times 10 to the negative 19 times 50 times 10 to the negative 3. And this gives us a value of 8.486 times 10 to the negative 4. Okay, and that gives us, meters is our pitch. Moving on, we are talking about the Hall effect, which is an effect that is described by an electric field. That is where a potential difference is formed when a magnetic field is being applied to an electric conductor in the opposite direction of the flow of charge. So we're going to use these equations here. Right, and since we are dealing with with current, we know that our moving charges are electrons, so we're going to replace our QE and our QVB with E in our charge. So in that case, we see that our elementary charge cancels out. E equals VdB, and we're replacing our velocity with our drift velocity because in our previous video we described that was the property that we use for current carrying wires. And that gives us Vd equals our electric field over our magnetic field. So since we know that our drift is also equal to this equation here, we're going to make our drift velocity equal to our right side of this equation. And once we do that, we can isolate for our number of electrons, which is equal to this equation here. Right, once we cancel out our other parts, and we're going to replace our A, this equation here, and our E with this equation here. So that gives us this final form. So if we wanted to apply this, if we have a conductive cube with side lengths that measure 1.2 centimeters, and it's moved along the y-axis with a velocity of 2.7 meters per second, and a 25 millitesla magnetic field directed along the z-axis. So first of all, that we know that our forces are acting perpendicular, so this is going to be a Hall effect, where this is the z-axis, this is the y-axis. What is the potential difference across the cube at equilibrium? I'm going to restart my explanation for this question. So first we want to find the direction of our magnetic force. So we have our particle here, right, and it's traveling upwards. And our magnetic field points, so if we had our velocity pointing up and we are curving our fingers towards the magnetic field, and since we are dealing with current, we know that the movement of charges are electrons. So we're going to use our left-hand rule because we are working with negative charges to find our force. So then our hand would look like this, with our force pointing this way. So this represents our magnetic force, and that means we have our electric force pointing in the opposite direction. Where this is positive and this is negative. So we want to find the potential difference between these two, plates in this case. They're acting as parallel plates. So we're going to use FB is equal to FE. So QVP is equal to QE. We're going to replace our Q with our electrons, elementary charge. So we're working with electrons. These cancel out. Sorry, this is not supposed to be here. So this is VB is equal to our electric field. And we know that our potential difference is our electric field times distance. Here, let me do this in a different color. So in this case, we would represent this by, we're going to plug in this equation here for our electric field times our distance, which is our side length. Okay, so solving for this gives us 2.7 times our magnetic field, which is 25 milliteslas, times our side length, which is 0.012 meters. And this gives us a potential difference equal to 2.7 times 25 times 10 to the negative 3 times 0.012, and this gives us 8.1 times 10 to the negative 4 volts for our potential difference. In this next section, we are talking about magnetic force on a current carrying wire, and in this case, we are replacing our value of Q with our value I times L over V, and this comes from velocity. So velocity equals distance over time. So that means time is equal to distance over velocity, right? So that's where our L over V comes from, where our length is our distance and velocity is the speed of our particles. So by plugging this into our equation, we get this new equation where our magnetic force is our current times the cross product of our length and our magnetic field. So if we were to use this in an example, if we have a single conductor in a power transmission line, so we have our length, and the current is moving from east to west in this direction that's indicated here at 80 amps, so we have our current, and we have our magnetic field. We want the magnitude and direction of our deflecting force. So since this is the movement of electrons, we're going to use our left-hand rule. So we're going to point our left hand in the direction of our current. And we want to find the direction of our magnetic field. So no magnetic field points from north to south, but they are going to point this way because this is geographic north and not magnetic north. And we know that on a compass, it aligns with our magnetic field lines pointing to geographic north. So that's why we have lines pointing this way. So once we turn them towards, we'd have to rotate our hand. So then our thumb is pointing up. So in this case, our force points upwards. So force is upwards, out of page. Okay, and if we use the equation, which is also equal to saying our magnitudes times sine theta, the angle formed between is 90 degrees, so we can get rid of our sine theta because that's just going to be equal to 1. So this is equal to 80 amps times our length, 40 meters, times 2.0 times 10 to the negative 7 teslas. This is equal to, so it's 80 times 40 times 2 times 10 to the negative 7. And this is equal to 6.4 times 10 to the negative 4 in our positive k hat direction, newtons. And in this third example, we have a wire that is experiencing a magnetic field from two magnets, and it experiences a force up and out of the page in a 1.25 Tesla's magnetic field. So what's the magnitude and direction of the current in the conductor in this case? Okay, so in this case, we have a magnetic magnetic field that points from our north to our south along this red line here. So if we pointed our thumb up and out of the page and curled our fingers towards the magnetic field, we would see that we would be traveling from left to right in our current. So again, we're going to use our equation, which is our current times our length and our sine. So we're going to assume that it's 90 degrees given the question. So this can just go away because that's just going to be equal to 1. And this is, so we have our force, so let's isolate for our current, which is equal to our force over our length times our magnetic field. And this is going to be 0.023 newtons. This is 0.05 meters. And this is 1.25 Teslas. And this is equal to 0.368 amps. Left to right. Okay, and in this last example here, for this note section of this video, we have a 30 centimeter long conductor with a certain mass, and it's suspended horizontally in a magnetic field. So what's the minimum current that's required in order to have our forces balance? So this means we have a wire. We'll redraw that. That is suspended, so that means our gravitational force wants to pull it down, but to balance it out, we need an upwards force for our magnetic force. So that means we're going to make our magnetic force equal the gravitational force. So we're going to use, our current times our length and magnetic field. This is times our gravitational force, which is our mass, times our gravitational constant. And this is, what are we looking for? We're looking for our current. So we're going to isolate for our current, which is this equation here. And when we determine that, this is 20 times 10 to the negative 3 kilograms. Our gravitational force is 9.81 per second squared. This is over our length, which is 30 centimeters, so that's 0.3 meters. This is times 0.12 Teslas. And this gives us a current equal to -3 times 9.81 divided by 0.3 times 0.12. And this is 5.45 amps. So that's the amount of current that we need to run through that wire in order to keep it in place in this scenario. Okay, so that brings us to the end of the notes section for week 8 of Physics 259. And in our next video, we will be running through some example questions relating to these topics. Thanks for watching, and I will see you in the next one.